great pleasure, Omer Bobrowski from University, who will be speaking to us on maximal cycles and random geometric complexes.
Right. So I'm going to talk about joint with Matt Kale from Ohio State and Primoz Krab from Lev Stefan Institute. The hopefully clear as we go along. I want to start with an introduction, sort of place this work in context and give you a little bit of motivation to what we are studying and why. And then more formal about what the exact object we're studying and what is the exact problem we're trying to solve. Before stating the that we have the main result, we're going to take a short detour and I'm going to tell you a little bit about what data about the probabilistic theory of random geometric complexes. This is quite helpful for us later on when we talk about things like persistent homology and complexes and so on. And I'll talk about the main result of this work, which is a description of the behavior of cycles, so to speak, in persistent homology generated by geometric complexes. So I start with the introduction. So we'll be looking at our simplicial complexes, which I'm sure well known to people here. Basically, we have a collection of vertices, edges, triangles, tetrahedra, and so on. And there are some rules by which we can glue them together. Kind of generalizing the model of a graph, where every type of object we have here has its own dimension. A vertex is 0 dimension, edge 1 dimension, and so on. Now, before I move on, I want to, so we're going to talk these objects when they are created at random. The question I want to try to address is, why should we care about this kind of random complexes? And we tried some motivation. The first one comes from a pretty common question by now in TDA. You can call logical inference maybe. What we're trying to do is there is some space to say something about, and we'll give finite data points from it. For example, maybe we have an annulus, and we want to say that this has one connected component and one hole in it. And is how to do that given a finite set of points. And one pretty common way to do that is to cover each point with a ball and look at all these things. And if we do it properly, then we get the right answer. So the balls here also give you one connected component and a single cell or hole. Now, as far as how to actually implement these kind of things in software, then working with actual geometric union of balls, that's going to be quite hard to into software. But if you do some translation into objects like simplicial complexes, then work with lists of vertices, edges, and so on. You can think of it as some kind of a translation, and then could be in this kind of object much easier. So we mostly think about simplicial complexes. Now, there is kind of problems. So first of all, all that I present here depends on how I choose the radius. So if I take a very small radius, all I see is just a bunch of components, probably the answer I'm looking for. If it's bigger, then I have a connected component, but there is a hoop here that maybe are about so much, and the radius is too big, then I lost all the information that I have. That's one problem. So what sample size do we need to answer certain questions? For example, with only 2 points, we can never find it. Finally, maybe more important is how to handle noise in such models. So assuming that points are not exactly where we expect them to be, they're moving. In any case, all of these problems, out of the randomness that we have in the data, and work with simplicial complexes, we better first see how random simplicial complexes behave and to understand that. So that motivation and from studied area of random graphs and networks. So probably, I mean, the first random graph model, and probably the most well-known one, is the Ardèche-Renyi model, where n vertices and you connect each pair by flipping a coin independently. And this model is simple to describe. but the flavor of this model and the theory that it has is pretty quite and well developed. And it also has a lot of applications in areas like network analysis, but also combinatorics and so on. One drawback of this particular model is that it's too much independence. So if you think about this thing as trying to model a network, the model tells you that if you know something that happens in one particular point in the network, it has no effect whatsoever on the rest of the network, which is probably something you don't really expect in the real world. So any other models for graph models for random graphs, trying to answer different kinds of properties for networks. One which is of particular interest to us is called the random geometric graph, which we'll see a bit later. This comes from a completely different source. So you start with a set of points which are random by themselves. There's some metric space, and then to connect them, we measure distances. So 2 points are close enough, meaning the distance below some threshold. Then we connect them, and as we don't. And so we call the random geometric graph. As far as folks are concerned, then this is a bit more realistic than the previous model in the sense that if you think about this as modeling, for example, social network, then if you know that X and Y know each other and Y and Z know each other, then it makes it more likely that X and Z also know each other, which is something that you do have in network models. One common application for this kind of model is in the area of wireless network, where we think of the vertices as a transmitter and to connect with others in this area. Then would be the range of each of these nodes, and then the graph gives you the connectivity of this network, and you can ask questions about passing along or dealing with interferences and so on. So then the application is pretty well developed, but at the end of the day, what graphs provide is a model for the pairing between nodes in networks. So you can see whether two computers or two people are connected. If you employ efficient complexes, then you have more flexibility to describe higher order interactions. So just a cartoon example. So if you think about either social or computer networks, so here can be either the name of a person or a name of a server or something like that. So you model a network by simplicial complex. You can not only say whether two people or two computers are connected, but also for this group of three people maybe collaborate together, or maybe you have four computers in the same network or something like that. So simplicial complex gives you an ability or a language to describe more order of interactions in networks that hopefully will be very useful for net modeling, finding phenomena and comparing different models and so on. So just to give you a motivation, why should we care about random simplicial complexes? Study of properties. The main tool we're going to use is homology, which sort of extends the sort of convergence cycles from graphs into higher dimensions. Briefly, you have homology that you take a space, and then you have a set of groups in dimension where error corresponds or represents the connected components in their space, and the dimensional homology groups represent k-dimensional holes or k-dimensional cycles. In most cases, we are interested in the Benny numbers, which are the rank or the dimension of these groups. We just count how many components or how many cycles we see in the space. Quickly, a few examples. One connected component, no holes. Beta 0 is equal to 1 and does nothing else. We have one component, but also a hole, so we're saying that beta 1 is also 1. In the sphere, it's just the boundary of the ball. Then the air pocket, the body inside the sphere, is considered a two-dimensional cycle. Every one-dimensional loop will on the sphere. We can show points, therefore the dimensional cycles, and beta 1 will be equal to 0. And torus has one connected component. There's no pocket or the void inside the is considered a two-dimensional cycle. And as far as the cycles are concerned, and those goes on top of the torus, and a different goes on the side of the torus, and therefore in case we say that beta 1 is equal to 2. In a nutshell, this work will be interested in persistent homology, which also I assume people are well familiar with. Persistent homology is to, instead of just looking at one snapshot, one space, we look at nested sequence spaces. For example, we look at the growing groups and draw different union of balls for different rays, and we want to see what happens to homology as we induce and presented it by using these barcodes. So we have a barcode for 0 for the connected components, and also barcode 1 is for the one-dimensional cycles. And about each of the features you see, each of the cycles that show up, when it showed up and when it disappeared or got filled in. So for example, look at the first radius, and I see a lot of connected components, but there's nothing else. Most of it connected. At snapshot, we can see that there are 2 components by now. The one whole tiny one here, which is going in pretty quickly, so the corresponding yellow bar here is pretty short. Moving then, we have by the single connected component, and everything else was merged, and 2 cycles, one which is really small over here, and a big one that is represented by the relatively yellow bar. Moving is almost filled in. We are left with just one connected component, one cycle, which is probably the answer we were looking for when we took the test. And radius is filled in, and we are left with just single connected component. So that's the main idea of persistent homology, and the barcodes are represented using persistent diagrams. The main idea or the motivation is that if we see a bar that or a feature that exists for a very long time, or a long way, then probably it means something significant about the underlying space that we want to say. But the question is, is it significant? How do we determine what is a significant feature, what is a significant cycle, and how can we quantify it in terms of statistical significance? And the main question we were trying to address in this work, and we'll get to the solution later. Which is the result we have so far. I make the problem relation more formal and describe exactly what are the objects that we are studying. So we'll the 2 probably most popular geometric complexes. The first one is check complex. So you have a set of points. You also produce R on each of the points, and then you're looking for intersections. Every pair that intersect, you place an edge. And the geometric graph, because it basically tells you that 2 points are close enough. Then 3 balls that intersect, like left. And 2-dimensional simplex on the 3 balls do not have a point in common. You leave it empty and move high in dimensions. At the end, you can throw away the balls, and you're left with just the carrier object we call the check. The reason, or one of the main reasons why this complex is interesting for us, is coming from what is called the Neves theorem or the Neves lemma, where we think about the union of the balls that we used in the previous slides to construct complex. Then that this and the check complex are homotopy equivalent, namely they are very, very similar as far as topology is concerned, and in particular have the same homology. And it's from the picture, because what you see here is that we have one connected component, also one hole here, and the same on the right, even though the objects are very, very different in nature. This is used for us for many reasons. One is that it tells us, and what I mentioned before, we want to ask questions about the union of the ball. The question is, how do we translate that into something we can code in software? Then the text gives us a good answer on how to do that. And from the point of view of theory, sometimes it's easier for us to prove things on the geometric shape, especially if we want to talk about coverage. And sometimes we want to count things, and then combinatorial objects like the complex are more helpful for us. And we can back and forth and remain the same. Sorry. We start the Viator-Rips complex, which is very, very similar. we start with the points, we cover them with balls. For action, we place an edge. This comes in the higher dimensional simplexes, where we don't require all the balls to have a single point of intersection, but we require only to have all the pairwise intersections there. So here, also on the right, we have all the pairwise intersections. Therefore, we place this simplex well, this two-dimensional face as well. And you can go in higher dimension, and you get another type of complex, which is slightly different. Just a few useful facts that might use us in the later on. So first of all, we would set up usually in some Euclidean space or some manifold. Even if the dimension of the point is fixed to be d, the simplexes that we create might be in higher dimensions. So the simplicial complexes we are constructing are abstract simplicial complexes, and the dimension is bounded. As far as homology, since their lemma tells us that the Czech complex is the same as the union of the balls, then we don't expect to see any homology in the complex for dimension d. An interaction between rips, which you can think of as that one can use to approximate the other. For example, you can bound the Czech complex between two instances of rips complex with the same set of points, just slightly modifying the radius. And this is useful in many, many cases. Sometimes for computational reasons, it's easier to work with the rips or the Czech, and you can use one to approximate. As connectivity is concerned for this complex, the one-dimensional skeleton is the same thing. In both cases, it's just the same geometric graph we were describing before. And so the questions would be exactly the same for the small. Now, everything was deterministic. I want to describe the probabilistic framework we were working with. So with a density function, which can be defined on either Euclidean space or some manifold, which allows us to generate points at random. And using the function, we generate a sequence of points which are IID, namely they are independent and have the same distribution. This model, there are two weighted ones. The first one we call it a binomial process, where what you just fix an n, and then you generate n points, or the first n points from the sequence that you generated. And it's known as the Poisson process. It's slightly different here. The number of points that we're using is random by itself. So you generate a random variable, your Poisson distribution, and then take the first n or any of the first n points. This model is more complicated, maybe, but these models are pretty much equivalent. Almost everything you can prove to one can be proved to the other. They behave very, very similarly, and there are methods to translate statements from one to the other called Poissonization and Poissonization. One very important and useful property of the Poisson process, which makes it somewhat attractive, is called space dependence. So two sets in the space A and B that are disjoint, the number of points and everything that happens to the Poisson process inside those sets is completely dependent. Therefore, if we ask any questions about what is happening in this set, no effect of what is happening there, and sort of it allows us to split up question or maybe into smaller problems, and that's very useful when we try to do some analysis. For the ultimate goal we would want to answer. So we have ways to generate point processes or models all depend on the density function. And in the density function, we can answer quite a lot of questions about the distribution of the points. But now we take these points and we generate either the barcode, or if you're more comfortable, you can work with persistent diagrams, where each cell is trying to a point in the x and y system, where the x is the birth time, the first time it appears, and the y is the death time. Now, what we would like to do is to say, given that we know how the point is distributed, what can we say about those diagrams, the barcodes or the persistent diagrams? What about the distribution of these objects? The number of bars, the length, the positions, and so on, or the points, and so on. The problem is that this mapping, starting from points in a metric space and translating it into this barcodes or persistent diagrams, going with the algebraic topology of everything, the analysis of the probability measures is very, very difficult. And at this point, we don't have a good way to put our hands on what distribution that we expect to see here. So we hope to get closer to in the future, but what we try to do in this work is to an easier or smaller problem. Simply, and that is so. Usually, codes, or way people look at it in cases is based on two types of features. One is the signal or the truth that you're seeking, or the significant features represented by the long bars or the points away from the diagonal, which I mark in green here. Everything else considered as knowns, which come maybe from the fact that we have only finite samples, and represented by the red things here, short bars or the points to the diagonal. And what we like to address is what can we say about the maximal persistence, or the longest, the picture that we see that comes from the noise part. So if we want, out of all red small bars, we want to sum about the bigger one that we see, or the one that is farthest away from the diagonal. Now, why this object? Because if what is sort of the most extreme for the last cycle that we can see from the noise, then we can use that to do some filtering, or maybe construct confidence intervals, this testing, say whether a feature that we see is significant or not, and so on. That we're trying to see in the context where the points are generated at random. If we move on to describe the results, I want to take a short detour and tell you a little what is known to date about just the models themselves, the topology of random geometric complexes. Now, the main goal of what we're trying to achieve here is to take either the check or Rips complex constructed from a random set of points, and in the limit, same thing is done over the place in random graph theory and so on. Take the number of points to infinity, and you don't want to have too many simplexes, because otherwise everything is going to get filled in, and it's not going to be very interesting. So we think the radius to go to 0. So it's sort of everything is under control. Now, I want to show you a short animation of the process, how it looks like. Idea of what it is. So here I'm generating points on the surface of the torus. Okay, and the time here is n, the number of points. Every time I'm adding more points, I have a smaller and smaller radius. I get up. And the union of the balls concentrated around the torus. Hopefully, at some point, okay, I stopped here. Then we get something that covers the torus and probably looks like the torus that I got the shape in the middle. So that's sort of the process that we're looking at. We're adding more and more points. We're taking smaller and smaller radii, thinking that if we do it properly, then we might see the underlying shape. Now, the point is the result that we're going to see at the end highly depends on how fast we'll take radius to 0. So suppose that we start again with the same process. We're adding more and more points, but now the radius go to 0 very fast. You can tell that this comes from a torus. You just see a bunch of disconnected particles, and the behavior is quite different. We do this thing, but now sort of in a rate which is not so fast but not so slow, and what you get is another kind of structure. So here it's not parsed as before. Things are getting connected. There are even large components, maybe so small cycles that are getting created, but it's the same as what we started with. It's not something that covers the torus and tell us that there is a shape of the torus here. In general, we differentiate between 3 different regimes: the sparse one, the dense one, and the dense one. And the theory shows that how this thing behaves. So with the regime, we call the first one critical and supercritical, and in between we have the critical regime. The first question is, how do we determine which of these we're at? And this is done by looking at the following term. We call it lambda, which is the number of points times r to d. D would be the dimension from one sampling form. D is a volume measure, and why this term is important here is because short calculation can show you that this is the expected number of points you see in a ball of radius r, and the number of points you see in a region will tell you the neighbor each vertex has. So this is of the degree of the number of neighbors you have. If it goes to 0, then everything is passed, hardly anything gets connected. If to infinity, then we have this dense structure. In between, if it's finite, we have this pretty behavior where we might have different size of components. Okay, so what I want to do, I want to give you a short review what we know about these complexes in each of the regimes, idea of how these things behave. We start with H0, the connectivity. That has nothing to do with the simplexes. It's just all about the underlying graph. So the result comes from the random graph theory. And briefly, what is known is that if we're at the sparse regime, the component is more or less the same number of points, which makes if we're moving to the critical point, the critical regime, the number of points is proportional to n, but it's smaller than n. So things get connected. There's a lot of components. The thing that shows up here is called continuum calculation, where if you lambda, and at some point a giant component shows up, and this is finally in the supercritical regime, it's not exactly known what's happening, but for sure it's not to have much fewer components than before. And the thing that we do know is that there is a phase transition here, namely a very fast change that happens, which the graph becomes very quick connected. And this is a threshold when the degree just from being slightly below log n times some constant slightly above it. Okay? We can translate to a state about the radius, okay, but we have a threshold such that slightly below it still have many components, and above it almost the graph connected. Now I want to talk about the higher dimensional homology groups. The behavior here is quite different. I just want to first point out why. So to think about connectivity, with zero, we start basically with just point. If it's very large and everything will get connected, and in between increase r, the number of components is decreasing. So we have this mono behavior every time we add an merge component. So we start with many points, we just get them more and more connected until we reach just one connected component. Homology groups is quite different. So at radius 0, we have no edges, no faces, so we have no cycles. If they're large, then even if we create cycles, they get filled in, so they're not all of them trivial. And here there is not monotone. Every time we increase the radius, we might create a cycle in an existing one, and it looks like that. So we start with no cycles, no holes. This we created a cycle here. Now we create another cycle. Now one of them got filled in, and so on. So the process is different, than connectivity and the analysis will be different. One thing that is going to be different is that for a continuous threshold, therefore when the graph becomes connected, here we have to see two different transitions. One, we start with a cycle and we see the first cycle showing up, and the other where we have all the cycles and all of them suddenly get filled in. Okay, so very quickly what we know of each of these regimes. So in the critical regime, the complex is very sparse, and more, if you have to see the construct cycle is going to be minimally isolated, minimal in the sense that it is the smallest number you need. If you think about the check complex, with one cycle, you need a triangle, an empty triangle. In a two cycle, you need an empty tetrahedron, and in just create a k cycle, you need k plus 2 vertices. For the triangle is not enough because you have all the pairwise sections. So to create one cycle here, you need at least 4 vertices to create a rectangle, a square. To create a two cycle, you need what's called a cross polytope, 6 vertices, and in general, you need different vertices, but still the behavior is quite different. What we can know is quite a lot. I mean, what the limit of the expression, the variance, also the limiting of the distributions, Poisson or for normal distribution, depend on the exact case. For the order of magnitude, how many cycles we have. So for it behaves like n times lambda some power. For the RIPS, it has a different power. Coming from cycles, we need different number of vertices to create those cycles. And in that, we have components at vertices, and as we go higher in dimension, we have fewer and fewer cycles, which makes sense because we need one more point to connect. Also, the first phase transition for the first appearance of cycles, what we have, which is check in the RIPS, comes from, we just examine the quantities here and we're asking when the quantity change from 0 into blowing up. And that's where we expect the first show up. And what we do is that if you're asking what is the probability that the homology, the case homology is not empty, if we solve threshold, they already have many cycles and the probability is almost 1. And if we below it, then the probability goes to 0. Sorry about that. Okay, so that's the condition where we expect the first cycle to show up. And very locally, it's not the constants, the values of will depend density and the space, but the general behavior is independent of that. In the critical stuff, we get connected, and therefore we might cycles which are not minimal, which require a lot of vertices, and therefore it is more difficult. We count, so lower bound would be the same number we had before, those minimal cycles, and upper one would be just a number of simplices, just coming from the graph. And we can just show that in order of magnitude we have order n components, but we don't have constants that appear. Also, look at the technion, they showed they law of large number and central limit theorem as well, even without knowing the constant. That's one Subag and Adler. What we can do here, even without knowing the constant, is analyzing the order characteristic. So it's generating some of the Betty numbers. In most theory, we can translate quite the Betty numbers into asking about critical points for the distance function. And without going much into the details, even though we don't know what the Betty numbers here, we can get formulas for the order characteristic. And then draw it and get some insights from it, which are useful both for and sometimes even for applications. Okay, the supercritical regime, the heaviest, the dense regime. So what we expect to see that a lot of connected and maybe covering the underlying space. To date require that we're sampling from a compact space, usually a compact manifold or convex in space. What we see is that the benefit coming from the critical regime where we have many of them, and when we cover the space, we expect to see finitely many of them. There should be some decay. A bit about that, but it still requires some analysis. But we recently did find the other phase transition we were looking for. At some point, we expect that, for example, if we're sampling from torus, if this is large enough, we expect to see only homology of the torus, and all more cycles should vanish or get filled in. And that we can call homological connectivity. And so there's a different threshold. To connectivity, it's the same scale of log n. It's a little bit different. And what we say, for example, is we can assume the probability that the atom check complex has the same homology as this we're sampling from or the torus. If we start off the threshold, there's still a lot of small holes that sort of interfere, and start off the threshold, it's almost guaranteed that we get the right answer. And of course, happen after the complex is already connected, so the constant is bigger. This section, so I just want to give you the picture of what we know. Sorry. So we have three regimes. The x-axis would be the radius, and this is a cartoon picture. And check complex. The RIPS is similar, but there are some differences. Activity, we know that at this regime, the number of components is almost n. Critical, it's proportional to m, but fewer. And then we call the decay to the point which we call the connectivity threshold, where suddenly the complex becomes connected. Betty numbers, so homology groups, they behave different. We start with no cycle, then at different points we see the different Betty numbers show up, and it happens very fast, so that we move fast from having no cycle into having a lot of cycles, represented blowing up to infinity. And here we know the distribution, we know the order of the magnitude, and so on. To the critical regime, not just the order of magnitude, but not the exact quantity. Critical regime, there should be some decay, which we know a little bit about. And what we know is that there's another phase transition where suddenly all the homology groups become identical to the space which we're playing from. And all of these and recent advances are you can find in a recent paper, maybe not so recent by now, but in a paper by that we worked with Matt Kale. Okay, now I want to move on to the method that I want to talk about. So we have these random geometric complexes, and we will think about homology and try to answer a question of what should be considered a significant cycle in persistent homology, or try to question and ask if we just have cycles that are created by chance and not due to any significant thing that we're looking for, what's the thing that can be created just by chance? So the setup that we examine, which should be the simplest one for this problem, so a homogeneous Poisson process defined on the unit cube. So we expect to see any significant feature that the cube has no holes in it. We're only interested in the cycles that occur to chance. P representing the K persistent homology of the barcode. Talk now on the check complex. I said at the end, what for the RIPs should be similar. We have a way to measure persistence, which is slightly maybe different than what many do. So, for example, we have the barcode here. So, we have the birth time and the death time. Instead of taking the length of the barcode, we're going to take the ratio between the death and birth. And that is a little bit why we need to do that. So, a measure of persistence. And fixing the dimension, we look at all the k-dimensional cycles and choose the one with the maximal persistence. And that's the object we want to study. Take the ratio rather than the length or the difference. One is convergence. So if we have this set of points organized this way, and if we just change scaling of that we're looking at, then we might see the same kind of structure but in a different scale. We will give all of them the same magnificence. But maybe importantly, that the measure is sort of prefers in the data rather than just size. I mean by that is that you have points, and you see that here you have many points organized very nicely around the circle, and have two what probably is just outliers. Two cycles. You have one cycle here, and you have another cycle here. Measure things by using distance, or sorry, the difference. And the structure here is very small, so the difference is going to be pretty small. But the relation between when the cycle appears and then disappears is very large. On the right, they are very big, and the difference is going to be big. But if you take it, it's going to be small. In many cases, probably what you want, if you find the set of points which is organized very nicely, it's probably significant to you than just 2 points, 2 outliers lying very far away from everything else and just creating this very large cycle. Therefore, it makes more sense to study the ratio. And it just comes from the analysis we discussed of random geometric complexes. Times occur during this critical regime we were talking about before, and the less time will happen in the supercritical regime where everything sort of gets filled in. And the sort of magnitude difference between these times, let's take the difference. Really what we're going to see is just difference in death time rather than the size. Whereas the ratio, we get a better resolution of what we're looking at. Okay, this is the main result that we have in this paper, which for now gives us not an analysis of the maximal size, but at least what the order of magnitude is. So again, K is fixed. We're looking at the K persistent homology for check complex. Take the maximum persistence for all K cycles. And the order of magnitude is going to be this delta K, which is log again to 1 of K. And with the upper and lower bounds, both with the same scale, but with constant. And this happens with a random complex, it happens with high probability, namely that the probability goes to 1 is the number of points going to infinity. That by now we know what the order of scale or the order of magnitude of this large cycle is, but we know exactly what the quantities are. So in the remaining of the time that we have, what I want to do is to give you the ideas how to prove this theorem, and I've got two different ideas, one for the upper bound and one for the lower bound, and I try to describe to you what we start with the upper bound. We can have a very large cycle, and the way it is that we should, if you want to construct a cycle with a very large persistence, it will require you to have components with many vertices, in fact, too many to be created using the model. And the main lemma that we're using is to use some kind of a isoproof lemma for cycles. What we stated here is that if you fix the birth time, so birth time is going to be R, and you fix a constant called P, then at birth time that the cycle appears, this the complex, if the persistence of the cycle is P, the complex needs to have a component with at least P to the K times some constant number of vertices. So in terms of the percent that we're looking for, we have a constraint to how many vertices need to be connected. Without proving, just an intuition for why this thing is true, think about one cycle. We want to have birth time be equal to R. So this P, the death time, should be R times P, this multiplicative persistence. If we want to create such a cycle with the fewest number of vertices, then what we need to take a of radius R times P, so that R times P would be the death time when we fill in the hole. And obviously around the circle, we're going to place balls of radius R. So that when we create a cycle is going to be at radius R, and the time that you fill in the circle is going to be R times P. Now, we need to, in order to do that. So, loosely speaking, right, the circumference of the big circle is 2 pi times RP times the radius, and the intersection between the small balls and the circle is the diameter is almost 2R, but not exactly. But in case, if you take the ratio between these two quantities, you get that pi is P, approximately pi times P number of vertices, which matches with what we have here. Okay, it's P to the power of 1. Cycle is the same idea. If you want to create the minimal structure that will provide such a cycle, you need to take a k-dimensional sphere of radius R times P and cover it with balls of radius R, and it's going to be the same. So the volume sphere is proportional to R times P to the K. The intersection is proportional just to R to the K, and then is proportional to P to the K. So we're proving anything about the constant, just to give you an idea. You need at least P to the K vertices to be connected in order to create cycles with high persistence. Okay, so just to show you what are the key steps for the proof here. So we said that this is our measure for persistence. We fix the birth time, we call it R. Now, if such a large cycle, then we just saw tells us we need to have this component at the birth, right? At least P to the K is a constraint on the structure. And the theory of random geometric complexes we discussed before tells us that there is a bound for the death time, right? Because the points such that all the small cycles are going to disappear and we're just going to cover everything. So death time are bounded. This is then over n threshold we see before. So if death time are bounded and we want to have a very large persistence, the only thing we can place is to take a very small birth time. But our birth time that the complex that we're looking at, the point where the cycle is created, is at a complex which is a very, very small radius. And so the components that we're going to see that are going to be relatively small. So we have two kind of contradicting requirements. We want to have a very large component so that we can create a large cycle, but we want to have a very early birth time, so we're going to have sparse complex. And sort of between these two restrictions gives us what persistence that we can get. Another lemma giving us a bound for how many vertices we can create for radii, and that's where the log n over log n thing came into the formula. So one statement about how many points we need to connect to create a large cycle. We have about how many vertices are connected, and we can combine them together. Then we get the upper on the largest persistence that we can, which is again this delta k, which consists of this log n over log n term. So this will be the main idea for how to prove the upper bound part. It comes from a completely different set of ideas. What we want to show is that there exists a cycle with at least a persistence of at least this quantity, okay, some constant. And what we're going to do, we're going to hunt for this cycle. We're going to look for it somewhere and show that it should be created at least somewhere in the cube. So we're generating a point in the cube. So what we're going to do, we're going to take this big cube and divide it into very small cubes. And zooming in into one of these small cubes, what we're going to be specifically looking for is that sort of like that. So we have the cube, which is the thing that is here, and in it we're going to look for a structure that covers this rectangular. And we'll get more details in a second, but we'll be for each of these cubes for what we call a floating cycle. And by that is that, first of all, we're going to show that the point that we have cover this thing which looks like a boundary of a k-dimensional box. So the boundary of the k plus 1 box is a k-dimensional cycle. It's floating in the sense that disconnected from the rest of the complex. So it lies entirely within this box and it doesn't make any connections outside. And it's important because if there are no connections outside, then there's no way that this hole can somehow get filled in. So we're going to, so the size of the box is 2, the size of this structure is going to be L, and we go ahead into smaller shapes, and the range between big L and little L, we're going to determine the persistence, and that's what we will be able to control. Looking for this structure somewhere in the big box. Now, a bit more details about that. So we have this is just one of the small boxes. So we're taking something which is an inverted version of the box, put it into very small boxes, and we name index them. And to look for, we're going to show that the single box inside a single point inside each of the boxes, that's for us. And to be precise, what we're saying is that if each of these small boxes we have a single point, and inside here no other points, and this tells us that we're going to create a cycle whose persistence is going to be proportional to the ratio between big L and little L, one constant. Now, why is this thing true? Done in a couple of minutes. Sorry. So first of all, if we take the smaller radius of square root over L and draw the balls of this radius, then each of them is going to cover its box. And so that structure is covered, so we can see the cycle. So it's covered already. On the other hand, if we take a large radius up to L4, the balls are not big enough to fill in the hole that we have here, and also not big enough to make connections outside the box. So it's still floating, and therefore the cycle still exists at that radius. And you can say that the birth time occurs for this radius, and the death time occurs after L over 4, and the persistence is going to be bigger than that. So there is one structure such that it has a single point in each box, then we're good. And so with the probabilistic event, EI would be the event that one of these boxes captures, and that a single point inside each of the systems we're creating a cycle. E would be the global event. So it's the union of all this event, namely it's the event saying that at least in one of the small boxes we create such a floating cycle. And then what we can prove is that by calculating and using the Poisson process properties, we know that if we get a ratio which is good enough for us because it involves the delta K we had before, then high probability the event E happens, which means that with high probability, this kind of cycle goes up somewhere in the big box. And that's what we want to check. And in conclusion, we can translate and show that we can find such a floating cycle somewhere inside the big box with a system which is bigger than this ratio, we can translate into the log n over log n, which is what we wanted. So it's a different argument than what we had before. We just looked for a very particular shape that creates a cycle which is good for us, but that's good enough for the proof. We also did some simulation. Primers did that where we try to see whether just by generating points random we see this kind of behavior. And what you hear, we have two graphs, one for one-dimensional cycles in two-dimensional points and dimensional cycles in 3D. The x-axis is not the number of points, but it's already the quantity that we're looking at. And there is a linear relation between this term and the maximal persistence. And it looks like it's going pretty much linearly. and it's true for quite many points. I mean, the largest sample here was 1 million points, which just translates to 5.3 here and 2.3 there. So it seems to be pretty consistent with what's happening in reality, which whenever you prove a theorem, that's something that you probably to happen. So just I talked only about the check complex, but for the complex, you can use this property of inclusion between of check and reps to show that the same happens as well. So if we have two values R1 and R2, one is a little bit after birth and one is a little bit before that. Draw this diagram of inclusions. So we have the check, the cycle appears here, it still exists here, and we have the sequence of inclusion between check and reps, so that if we have a cycle here and here, it should survive the transition over there. And so if the persistence of the check complex is bigger than some constant, for the reps complex it will be bigger, the ratio will be bigger by the same constant, but the factor of square root of 2, which for us it doesn't make a difference because we only care about the order of magnitude. Okay, so this one will work for the reps. This is the lower bound, but you can do the same argument for the upper bound. So to wrap up, well, the main statement is that we can compute the order of magnitude of the largest cycle that you expect to see that are created by chance, or the cycle show up that the noise parts in the diagrams rather than the significant one. So try to compare them to the significant cycles, to the real ones, right? If you have to say the cycle of the torus we're sampling from, then the depth is the constant. It just depends on the shape we're sampling from. The birth, we know by analysis of random geometric complexes, this happen, everything is covered, right? Before average threshold we had before, so we even the info bound for the birth time. Together, we say that the persistence of the true cycle is at least this quantity, n over log n, which is much bigger than the cycles of the noise, which is good. About kind of quantity to noise ratio in a way, how big the true cycle compared to the noise cycle, and we get some bound telling us that, enough points, then you can differentiate quite well. We need more analysis on that. And as far as future work, so this is just the first result, the first probabilistic statement we can make about persistent homology. We would make everything more exact and find the limiting distribution, go on to the shapes and different kinds of distribution, maybe calculate how many cycles are there when you have not only but also dynamic shape that you want to recover, and the exact comparison between the signal and the noise. And how can you translate that into statements for TDA? How can we use that to do hypothesis testing, or maybe confidence intervals that can be useful for TDA methods? And the problem relates to extreme cycles about sampling from compact supports. And the picture is that if some points and the radius is large enough, you're going to cover everything. In many cases, we're interested in this where the support is not compact, for example, the normal distribution. And in more and more points, you're also expecting many outliers. And the question is, what can we say about the persistence of the outliers? And that's a different kind of analysis, but it's also something we're looking into. Yeah, that's all. Thank you very much.
Thank you very much, Omer. Are there any questions from the audience for Omer? Well, in your concluding slide, you had true cycles. Sorry, I didn't understand what you were. What community go back?
We have it only for point samples from in a cube. Namely, objects we're looking at are just noisy cycles in persistograms. It's not what you consider significant. If you sample, for example, from the torus, so you expect to see these small cycles, but also to see bigger cycles that belong to the torus. And the question is, do what we calculate compared to the true cycle, right? And the small cycles that the parts scale like this thing, and is that we can also get some bounds to what the persistent of the true cycle, the one that you're actually interested in, would look like. And here we have bound to the scaling and do quantities, and then we you'll differentiate between the persistence, right? The persistence of a cycle, a significant cycle, compared to the persistence of the cycle of the noise, is becoming bigger the more points you have. So you have a sort of a better differentiate between what is significant and what is not. It's not a very analysis. It's just top of the head what we have at this moment, food that we already have.
That's very nice. Thanks. Also, so in your model, there's a certain over which you have homology in a certain degree. So how does that raise the size of that regime compare with the length of the maximum persistence cycle?
So actually, since we're taking the ratio and not the length, so what we found is that the beta that we see not survive all the way to the end, but other things that exist in the sub regime, the sparse regime. That's where we have the biggest sort of ratios. I didn't get so much, but here. So right here, that we're looking at for the upper bound, the best cycles that we find. That this is the lambda parameter that we had before, and this is that goes to 0. So that's the sparse regime. That's where we find a very large structure, at least from the ratio. So in the picture that we here, so if you take the of the bars, then the bigger cycle would be appearing here. But if you take here in this, but the big cycle that we find when you take the ratio actually show up here.
Okay, I see your mouse.
So you saw or not? I don't know. The last cycles in terms of ratio between death and birth, they occur in the subcritical regime on the left. Okay, in the scenario.
I thought they were born in the subcritical, but they died in the supercritical.
So I think if death time is happening in the subcritical, they don't need to get all the way to the supercritical.
Okay.
If you measure things using the difference, then it would be a whole different picture. But the cycle that we found, that they're contained within the subcritical regime.
Great. Maybe show us the numerical sliding the station.
Yep.
What do each of the blue points correspond to? One simulation, is that right?
Each blue point is an experiment with n points, n finished by the x-axis. And in each trial, we have n points. We generate persistence energy. We calculate the maximum persistence, and that value of each point is the maximum persistence that you have. So you have how points versus what is the maximum ratio. The number of points, the x-axis is already the quantity we expect to see. It's already the quantity that we want to see, and we see a linear relationship between log over log n and the maximum persistence that we find just by generating points at random.
Nice.
Yeah, sorry about that.
Thanks. Anyone else have any questions? Let's thank Omer again for a very nice talk. Thank you, Omer.